Good evening and welcome to our second public lecture in our Winter-Spring 2021 webinar series. As Laura said, my name is Amy Merkel and I'm a research scientist at LASP and the current lead for our Office of Communications and Outreach. It is my great pleasure to introduce you to our presenter this evening, Dr. David Brain. Dr. Brain is a research scientist at LASP and an associate professor of astrophysical and planetary sciences here in Boulder at the University of Colorado. Dr. Brain received his PhD from CU in 2002 and then spent 8 years at UC Berkeley as a postdoc and research scientist before returning to CU as professor in 2011. Dr. Brain is interested in the processes that cause planetary atmospheres to move to and from a habitable state. His research group uses spacecraft observations and computer simulations to study the escape of charged particles from the atmospheres of planets like Mars, Venus, and Earth. He is a deputy PI of CU's MAVEN mission currently orbiting Mars, the science lead for the Emirates Mars mission, for which LASP is a lead academic partner, and the PI of a new NASA-funded science team science center that he will tell you more about this evening. Thank you so much, Dr. Brain, for joining us this evening. I'll now turn the presentation over to you.
Great, thank you for having me. And let me start by sharing my slides and putting them into a view that works for all of us. Okay. So I'd like to tell you a bit about a question that has been guiding my research for the past couple years, and I'm hoping continues to guide my research for the next several, but also a question that I hope to find an answer to sometime before the end of my career. I don't want this to last forever. I want to know the answer. And that question you can see on the screen right now is it's do habitable worlds require magnetic fields? It's a 6-word question, so not very complicated, but there's a lot that underlies the answer. So let's dive right in and ask our first question: how do magnetic fields affect life? And the first thing that I tend to think about when this question comes to mind is actually not the research that you'll hear about for the rest of the evening, but I want to discuss this for just a minute. The first thing that comes to mind for me are homing pigeons. And when I was in graduate school, I heard a story about homing pigeons in the UK. And they have these things called homing pigeon races, where the pigeons are wheeled out into the middle of a field and released, and then they have to find their way to their destination. And people record how long it takes them to get there. And it turns out that homing pigeon races can have some problems. I can't imagine any problems that could happen with homing pigeons at all. That seems like it would be seamless and without ever any sort of difficulty. But indeed, there are some issues with homing pigeon races that are caused by nature outside of Earth. So this is a published paper that appeared in the Journal of Biological Zoology or something like that in Italian up here in the 1970s. And there was a notion that variations in the magnetic field of Earth may affect the biological activity of animals. And at that time, people had performed experiments by applying magnetic fields to an animal's body to see that their ability to navigate was inhibited when a magnetic field was applied to them. I'm not sure how we would get permission to perform those experiments today, and I'm not sure whether we would want that permission. But regardless, it had been noticed that for homing pigeon races, the ability of the homing pigeons to find their way home was influenced by solar activity, things happening on the sun. And one figure from that paper is shown here. And the horizontal axis is an indication of how active the sun was. On the right, the sun is very disturbed. On the left, the sun is quiet and calm. And the y-axis is the percentage success rate for the homing pigeons finding their way home. And you can see that when the sun is calm, most of the homing pigeons, or many more homing pigeons, are able to successfully find their way than when the sun is active. There are a couple of separate races that are shown in open circles, and those had separate problems going on with them. So if we take the acceptable data, there's a link, and the animal's navigation is influenced by solar activity. And that's believed to be through the influence of solar activity on Earth's magnetic field, making it fluctuate. As a matter of fact, this persists to today, or at least into the recent past. Here's a website for homing pigeons. It's the Royal Pigeon Racing Association. This may not have been updated since September 2014, but it's still, you can find it on the web today. And they post warnings about solar flares and solar storms for people who are working with homing pigeons. So it's a real effect. There are all sorts of other possibilities. People are starting to believe the link between certain animals and Earth's magnetic field and ways in which they use it. None of this has been proved conclusively yet, but sea turtle navigation, the ways that cows orient themselves in fields as viewed on Google Maps, sharks, bats, salamanders, and even tiny little bacteria that leave basically little mineral debris, have little mineral debris inside them that is magnetic. All of these are believed to respond to Earth's magnetic field. So this addresses the question of a way in which life interacts with a magnetic field, but it doesn't answer the question of whether habitable worlds require a magnetic field. If Earth's magnetic field went away, I'm pretty sure this sea turtle would continue to survive. So let's move on to another effect that you may be thinking about, which is radiation and the idea of Earth's big magnetic field as a shield for radiation, and radiation can be damaging to life on Earth. Why are these two linked in this way? And it's a relatively straightforward concept to link. That is, if you have a particle that has a charge, think of maybe static electricity or something like that, a charged particle moving in a region with a magnetic field takes right turns or left turns, depending upon whether it's charged positively or negatively. A particle without any charge, like this pen that I'm holding, if I were to move that in a straight line in space anyway, it would continue in a straight line forever and ever and ever. But as soon as I give that particle some charge, magnetic fields have some influence on where they go. And this is why there's a link between magnetic fields and at least some radiation. So it turns out there are several types of things that we lump together under one word, radiation. That's a word that I want to demystify here for just one slide. When we talk about radiation, we're not talking about a single thing. There are all types of radiation. There are X-rays and gamma rays and neutrons and particles that are called alpha particles and beta particles. These are all radiation, and they all have different properties and come from different sources. Not only that, they have different fundamental characteristics. Alpha and beta particles are charged particles, the kinds of things that magnetic fields influence. Whereas X-rays and gamma rays, that's light, the same as visible light or ultraviolet light or infrared light. This is just another kind of light. Magnetic fields don't influence how that light moves or propagates. And then neutral particles like neutrons, magnetic fields have no influence on those either. So magnetic fields only have an influence on some fraction of radiation that could be hitting Earth. Not only that, this diagram shows that different types of radiation have different abilities to make it through material and substances. If only there were a material or a substance above Earth's surface that could shield us from radiation. And it turns out there is. Earth has an atmosphere. And that atmosphere has thickness that decreases as you go up, but there's enough atmosphere here that it can attenuate or decrease some of the radiation that's coming from outside toward Earth. So this is painting a picture of magnetic fields maybe not having total control over the radiation environment at Earth's surface. Not only that, you can surf around and Google images on the web last night while you're preparing this talk and find several pie charts for how much radiation those of us standing on Earth's surface experience and where it comes from. So here's a chart from the EPA, and it turns out there are many different sources of radiation. And the radiation coming from outside, the radiation that could be influenced by Earth's magnetic field, only accounts for 5% of the total radiation that we would experience, at least in this chart. In some other charts, it gets up as high as maybe 11%. So a small fraction of what you or I or the salamander or the sea turtle would experience is actually coming from outside, and only a fraction of that is susceptible to magnetic fields. And even those particles, we still have Earth's atmosphere helping to protect us. So the link there between magnetic fields and radiation might be important on some planets, but it's not a really dominant factor here on Earth. So I'm going to move on from that topic and ask the question again, do habitable worlds require magnetic fields? So that forces us to think of how else life and a planet's magnetic field may be linked. So let's build up a chain together and explore this link. So the first link in the chain might be something like this. We know that all life on Earth requires liquid water to survive. There are millions of species. Haven't found one yet that doesn't require liquid water to survive. It doesn't matter if you're a ladybug or plant life or mold on an orange or even microscopic bacteria or my family on vacation, we all need liquid water to survive. So that's a requirement, at least a requirement for Earth-like life. And we don't know of any other kind of life so far, so this seems like a safe part of the chain to build. Let's add another link to the chain. It turns out that to have liquid water on a planet, that requires an atmosphere and a fairly substantial atmosphere. So here you can see the surface of Earth, actually in Rocky Mountain National Park at Bear Lake. Actually, this might be Enchanted Lake, where there is water existing as liquid, but you can also see solid water, ice and snow, and water vapor as well. You can see 3 different phases of water, solid, liquid, and gas, that can all exist on Earth's surface at the same time. And there's an important thing that I said there, and that is Earth's surface, and that's what we're talking about here. We're going to disregard life that lives below the surface of a planet. So that was a nice picture with different phases of water. Here's the kind of diagram you may have encountered in high school chemistry or even middle school chemistry. It's a phase diagram for water with pressure on the vertical axis and temperature on the horizontal axis. And in our daily experience, we're used to existing at a single atmospheric pressure and then experiencing a range of temperatures. Sometimes it's cold enough that most of the water is solid. Sometimes it gets a little warmer and we have liquid water. Sometimes it gets warmer again and we can have gas. And that's because we live on Earth's surface where there's a substantial amount of atmospheric pressure. On a place like Mars, however, which has much less pressure in its atmosphere is much thinner, it turns out that if you exist in a place like that, then temperatures could be such that most of your water is solid. And if things warm up, you skip the liquid altogether. You go straight to gas. Water is not stable as a liquid on the surface of a planet that doesn't have enough atmosphere to make liquid possible. So be thankful that we have an atmosphere as thick as we do. It enables us to be here since we require liquid water. And again, the assumption here is that we're thinking about life on the surface of a planet, and there are many fascinating worlds, even in our own solar system, that could harbor life beneath the surface and may even be a better place to support life than a place like Mars. But for now, I'm thinking about the surface. One more link in the chain here, and the last link that I'll add for now is where we'll spend the rest of our time. In order to have a substantial atmosphere, that may require a magnetic field. And there's a question mark there. That's what we're going to be exploring, and that's what I've been thinking about and will be thinking about for the next few years. So this is a famous diagram in some part of the science community, the heliophysics community, not a diagram, a cartoon, showing Earth with its big, strong magnetic field. and Venus, which is nearly the same size as Earth, but which lacks a magnetic field that is formed in the core of the planet and envelops the entire planet to great distances. Venus doesn't have a magnetic field like that. Mars is smaller than both Venus and Earth, and it also lacks a magnetic field. So we could just declare victory and all go home if we wish to notice that Earth has a magnetic field and is habitable. Venus and Mars do not have magnetic fields, and as far as we know, they are not habitable. Therefore, the correlation is proved and we're all done. Magnetic fields are required. Thank you and have a good evening, and I will now take questions. But a true scientist would feel really uncomfortable with only 3 objects on which to base their conclusion. So unfortunately, that means you have to keep listening to me for the next 20, 25 minutes or so. Okay, not only Earth, Venus, and Mars, like on the last slide, and comparing those, but this question has become increasingly interesting and maybe important in the era where we now know about thousands of planets orbiting stars other than our own, called exoplanets. And we don't have any pictures of exoplanets. They're too far away. And so we have to try to imagine what they're like and use alternative means to figure out what they might be like. And if we were able to determine whether one of these planets had a magnetic field, and we knew that magnetic fields were required to be habitable, that might be a way to help us learn or deduce more about those planets and figure out which ones are more interesting to us than others. This link is going to be constructed through the topic of atmospheric escape, which is one of the main topics that I've devoted my professional career to considering. Here again is another cartoon showing a very poor planet, which is losing atmosphere all over the place. It's visually pleasing, maybe, or chaotic, I don't know. But the different colors and the different styles of particles escaping are supposed to indicate that there are actually many different ways to make atmospheric particles leave a planet. There are many different mechanisms. And these curved trajectories involve charged particles, the kinds of things that are influenced by magnetic fields. Even some of these other mechanisms that involve the escape of particles that are not charged have at some point in their history been charged and therefore been influenced, have this process be influenced perhaps by magnetic fields. So we want to understand the relationship between magnetic fields and atmospheric escape during normal periods for a star, and also periods when the star is really active or has a big solar storm or a flare. There are some stars, especially in our galaxy, that are prone to doing this all the time. What are planets like that orbit those stars? Can they even keep an atmosphere in this kind of situation? So let's talk about magnetic fields and atmospheric escape and step back and give you the big picture argument for why they are important. So I'm going to argue that magnetic fields should protect atmospheres, that they are important. And I'm going to argue that based on simple physics and physics that I've already demonstrated in this talk. And Earth has a big, strong magnetic field, and Mars does not have a big, strong magnetic field. And these little yellow streaks here are supposed to represent charged particles flowing outward from the sun, the solar wind screaming towards the planets at 400 kilometers per second. And you can see that those particles get very close to Mars before they're deflected and go around, and they interact with the atmosphere, while charged particles at Earth never make it down to the atmosphere. And the simple physics that's at play here is the same physics I already showed you. Magnetic fields deflect the trajectories of a particle that has an electric charge. And these particles in the solar wind, protons, are charged positive. There are electrons in the solar wind as well. And they all get deflected around Earth by the big, strong magnetic field, while at Mars, that lacks a magnetic field, they get all the way down to the atmosphere and interact with it more directly. So what's the support for this idea that magnetic fields should protect atmospheres? Well, let's go to a NASA-created video. Those are always fun to watch. And so this video is built around work that comes from the MAVEN mission, a mission that's orbiting Mars now to study atmospheric escape, and that the University of Colorado leads and that I'm involved with. And in the videos, you see the solar wind flowing towards Mars. And then based on some animations that are based on simulations by a colleague of mine, Xiaohua Fang, you can see how charged particles should be leaving the atmosphere of Mars, colored according to their energy, where red is a lot of energy and blue is not very much energy. So this is a prediction from a simulation, but a member of my research group, when she was a postdoc, Yashui Dong, actually constructed, using MAVEN observations, the paths and energies and abundances of particles that are actually leaving Mars. And the map that she created is shown here, and it matches this simulation, at least qualitatively. We can see that particles are leaving in the same direction that the simulation predicts, and that they gain energy as they leave the planet. So we can use maps like this to tell us that Mars lost a lot of atmosphere over time. When we add all of this up, not just from this process, but some of the other atmospheric escape processes that I mentioned existed earlier, we think that as much as one Earth atmosphere, somewhere between half an Earth atmosphere and 1.5 Earth atmospheres has been lost from the planet Mars over time. This is important because Mars has a thin atmosphere today, but on its surface, we see dried up riverbeds, dried up lake beds, all sorts of evidence that water used to exist as a liquid on the surface. The escape of atmosphere to space is a way that Mars could have lost an important amount of atmosphere, an amount of atmosphere that would have allowed it to be habitable billions of years ago. So magnetic fields should protect atmospheres. Unfortunately, I am going to move to the next slide. Unfortunately, magnetic fields also should not protect atmospheres because it's simple physics. I'm sorry to relay that to you, but that is the case. And the general argument is that Earth is a pretty small little planet in this global perspective of the solar system. And if we think about the amount of energy from the sun, the amount of material from the sun that would have intersected Earth in the absence of a magnetic field, it's relatively small. But as soon as you put a magnetic field there, Earth looks really big in the solar system. It interacts with a lot of energy coming from the sun, a lot of material. And even though that material doesn't make it all the way down to Earth's atmosphere, the momentum or the energy from that material can make it down to Earth's atmosphere. It's transferred along magnetic field lines, and that energy gets deposited in the atmosphere. And we know that this happens because we see aurora happening on Earth. That's a consequence of that energy deposition. So this situation I think of as the sails on a ship sort of explanation for why magnetic fields might not protect atmospheres. They're actually presenting a large cross section to the energy from the sun. That energy gets collected and then can drive the escape of Earth's atmosphere. And that escape we measure coming out of the polar regions, the same regions in which aurora are occurring. And we've measured this with spacecraft. So that's one piece of evidence for why magnetic fields should not protect atmospheres. A spacecraft called FAST orbited over Earth's poles and made lots of measurements in these polar regions where atmosphere is escaping. And a colleague of ours named Bob Strangeway many years ago made a plot like this that shows that the amount of energy that's being deposited into Earth from the solar wind is strongly correlated with the amount of atmosphere, the number of ions or charged particles that are escaping from Earth as well. And this correlation suggests that the solar wind has an influence on how much atmosphere is escaping. If the magnetic field were protecting the atmosphere completely, the solar wind maybe shouldn't matter, but this shows that it does. There's an asterisk there that I'll skip past, but I'm happy to talk about. Another piece of evidence comes from comparing Earth, Venus, and Mars. So in this diagram constructed by another member of my group, Robin Ramstad, you can see observations from various spacecraft orbiting Earth, spacecraft orbiting Venus, and spacecraft orbiting Mars, all shown to scale, where the warm colors suggest a lot of atmosphere, a large flux of particles is escaping from the planet. And the qualitative picture here isn't so important. The main 2 points are, number one, we've measured atmospheric escape at all 3 planets. And number two, those atmospheric escape rates are about the same. To within an order of magnitude, Venus, Earth, and Mars are all losing the same number of charged particles every second. If Earth's magnetic field was so important for protecting the atmosphere, you would expect its escape rate to maybe be a lot lower. So we have these 2 ideas based on simple physics, and we have to figure out which one is correct. So how do we get out of this situation? Well, I'll spend the rest of my time telling you about an effort that's ongoing right now and that is just beginning in the community. So there's a team science center, and this center is virtual. And it's made up of 17 scientists from around the US and from around the world. And it's called MACH. And MACH stands for magnetic fields, atmospheres, and the connection to habitability. And it's a science center that several of us thought was a good idea. And so we got together and I ended up leading the proposal. And it's been funded by NASA for as many as 7 years. So we're nearing the end of year 1. We're probably 2/3 of the way through year 1. And at the end of year 2, we can re-propose to NASA and see if we can get 5 more years of funding. There are 9 science centers that have been funded for the first 2 years, and then they'll down select at that point and only pick about 3 to move on. The good news is 2 of those 9 science centers are being led here out of LASP at the University of Colorado. So the MACH Science Center is what I'll tell you about, and it's designed to answer the question, do habitable worlds require magnetic fields, with a focus on atmospheric escape? As a science center that's working to make a plan and do its work, we have to write things like mission statements. This is the only slide you'll see like this, but we've just recently constructed our sort of draft mission statement. And there's a lot of hidden and underlying meaning in these words, but this gives you a broad sense of what we plan to do, which is construct a framework, a way of answering the question that allows us to evaluate atmospheric loss from any rocky planet, even one that we make up in our heads, as long as we provide the relevant information about that planet and the star that it's orbiting. So that's our goal. And hidden in this is the importance of the magnetic field. If the magnetic field is strong or weak or non-existent, how does that change our answer? So we have 2 or 3 different approaches that we're pursuing right now. And our goal is to mesh or merge all of these approaches in the center. So I'll tell you a little bit about each one of these approaches. Maybe approach number 1 is through comparisons of Venus, Earth, and Mars, like that slide I just showed you a couple minutes ago that had the observations from all 3 planets in the same place. And I told you that the escape rate from all 3 of those planets was to within an order of magnitude the same. However, I'm not sure that we can make a statement like that with confidence. So you're seeing something on the screen and you're hearing what I'm saying, and those are going to be different for the next 30 seconds. So maybe listen first, and then we'll watch together. It turns out that Venus, Earth, and Mars were visited by different spacecraft with different instruments in different orbits, all making measurements. It's hard to compare those measurements with each other without being very careful. Not only that, if we those missions orbited the planets in many cases at different times, and we know the sun varies with an 11-year cycle, and we need to be careful when we're making those comparisons to have accounted for that. Finally, if we look at what's on your screen right now, I'll make the last point, the reason that this is not a very easy apples to apples comparison between the 3 planets. This is a computer simulation of the inner solar system with the sun at the center. And you can see the location of Earth and Venus and Mars around the sun and some important spacecraft. And this simulation shows basically the solar wind flowing outward from the sun at a time when there's a big blurp of material coming from the sun, a solar storm. And you can see that those solar storms hit some planets and not others. And even at quiet times, you can see that the planets experience different conditions. Venus is always closer to the sun. Mars is always farther from the sun. So they start off experiencing different things, and comparing the escape rates of those 3 planets directly is problematic. So we're starting to make some of those corrections within our group. And I have many great people working in my group, and I can't show results from all of them tonight. So you'll see results from 2 or 3 of them tonight, but please understand that there are 8 or 9 really great people in the group doing really great work. So here's one result that shows the solar wind intensity on the horizontal axis and the escape rate on the vertical axis. And for Mars, as the solar wind becomes more intense, the escape rate kind of goes up and down according to our measurements. It responds to the solar wind in this way. Venus, very close to the sun, never experiences really weak solar wind like Mars does. But for the solar wind that it does experience, there's this positive trend: stronger solar wind, stronger escape. And for Earth, which is kind of in between the two, there's an incredibly strong response. The escape greatly increases when the solar wind only increases a little bit. The 3 planets respond differently to the solar wind, and part of our job is to figure out if this really strong response of Earth is coming because it has a magnetic field and the other 2 planets do not. This plot, by the way, is just based on 4 published studies. That's it. And I have a really talented undergrad named Maddie, who has had the thankless job of mining the literature. And she's made a spreadsheet of 120 publications that have escape rates for these 3 planets, plus other objects like Pluto and Titan in her database. And so we're going to mine the entire database to try and get even more information out about how these planets respond to the drivers from the sun. Okay, that's approach 1. Approach 2 is forget Earth, forget Venus. Let's go to Mars and just think about Mars. That seems fun. And I have a lot of experience studying Mars, so I have some bias there and some reason that I'd want to do that. But let me justify why I think that's a reasonable thing to do. Number 1, we have this spacecraft that you've already heard about called MAVEN, and it's been orbiting Mars since 2014, studying the escape of the Martian atmosphere. As a matter of fact, I'm going to argue, and since I can't hear you, you can't really argue back, so therefore I must be right, that MAVEN has the best observations of atmospheric escape of any spacecraft in the history of the solar system, and therefore the best observations of escape are coming from the planet Mars, as opposed to the planet Earth or Venus. Our best information is at Mars. Lots of relevant data. Number 2, I think Mars is a Rosetta Stone. When we compare Venus to Earth to Mars, if we discover there's some difference in atmospheric escape between those planets, it could be because Earth has a magnetic field and the other planets don't, but it could also be because one's closer to the sun than the other, as I said before, or they're different sizes, or they have different atmospheric compositions. It's hard to positively state that any differences come from a magnetic field. But Mars carries magnetic fields of many different strengths all at once in the same place. And that's because Mars is unmagnetized like Earth. It has no big global magnetic field like Earth does, but it has regions of the crust that are very strongly magnetized. Some regions with the dark colors are really strongly magnetized, 10 to 20 times more strongly magnetized than Earth's crustal material. Other regions are weakly magnetized, and still other regions have no magnetic field at all. We have a built-in control experiment. We can study escape from strong regions, moderate regions, weak regions, and unmagnetized regions on a planet with a single size and a single atmospheric composition at a single distance from the sun. We can isolate we can control for all the other variables and just isolate the magnetic field. So what are we learning so far? Well, I'll show you 2 results here. One from the oldest member of my group, maybe. No, not the oldest member, but one of the senior members of my group. It's actually me. It's me in the group. And so taking MAVEN observations, we can map the observations of escaping atmosphere from Mars on some sort of spherical shell surrounding the planet and figure out how much atmosphere is escaping. And then we can make different maps. And we could make a map when Olympus Mons, the big volcano, or the strong crustal fields are facing the sun, or turned 90 degrees from the sun at dusk, or at midnight, or at dawn. And we can examine how the escape rate changes as these big magnetic fields face the solar wind or face away from the solar wind. And we see that there's some small variation in escape, but that variation is less actually than the uncertainty in our averaged measurements. So any effect there has to be really small of the crustal magnetic fields at Mars. Maybe they're not so important. This is a global measurement from the whole planet at once. But if we zoom in and just look at escape coming from above individual regions, then I have a graduate student that just defended this past summer that looked at that. And I'll orient you on this plot. The horizontal axis is the strength of the magnetic field at Mars. So let's just look at the top part of the diagram. The vertical axis is altitude, and the color is how much oxygen is escaping from the planet. And we see that above strong crustal magnetic fields, there's a lot of oxygen escaping from the planet. And above weak crustal fields, not so much. So and unmagnetized places as well. So it seems like the strength of the magnetic field does play some role in how atmospheric escape works at Mars. Maybe they are important after all. Okay, third and final approach before we start to wrap up is not using observations at all, not observations from Venus, Earth, or Mars, not observations from just Mars. Let's use, computer simulations. And I know that Wally, technically he's a computer. You would think of him more as a robot, but I'm the one that got to put the figure on the slide, and I like Wally. And so for the purpose of this slide, he's a computer and he's going to save us. But really what I mean are computer simulations. So we have simulations, and this is an older one, but we have very active simulations going in my group and groups within the MACH Center, our colleagues within the MACH Center as well, that simulate how atmosphere escapes from a planet. So here's an older simulation from a colleague in Japan, and these arrows sort of indicate which way particles from the solar wind are moving around the planet Mars, I think, for this one. And the rainbowy colors show escaping atmosphere in the simulation. So by putting the appropriate physics in the simulation and making sure we've characterized the atmosphere appropriately and the solar wind appropriately, we can predict how much atmosphere should escape from a planet. And in the MACH Center, we have actually many models. And we're hoping to compare these models to each other, number one, and we're hoping to merge them together into a supermodel, number two. So we have several models for people who model unmagnetized planets like Venus and Mars. And these aren't modeling the same conditions. These are just supposed to be pretty pictures. But we have models that will simulate atmospheric escape. There are also models that simulate atmospheric escape from magnetized planets like Earth. And it turns out these two communities, the magnetized planet community and the unmagnetized planet community, started diverging a couple decades ago. Their models no longer have much in common with each other. They've had to make very different assumptions in their models. And there's some really good assumptions in the unmagnetized models. And there's some really good assumptions in the magnetized models. And we'd like to make a model that is the best of all worlds and that could model a magnetized planet and an unmagnetized planet equally well. Then we can put in any planet we would like. But we have to make sure that those models are correct, and we do that by comparing with observations. So a preliminary result right here, I have randomly selected the one model from my research group. And again, this is a past graduate student from the group, Hillary Egan. She took her model and she ran it several times, and each time she ran it, she increased the strength of the magnetic field from the planet. And you can see that if you were to draw the magnetic field lines around that planet, the magnetic field lines look different in each of the 3 different situations as we increase the magnetic field. Turns out she ran this simulation 7 times. And so here's a plot showing the results. Horizontal axis is the strength of the magnetic field, ranging from no magnetic field to a stronger one. The vertical axis is the escape rate in some relative units. And we expected that either magnetic fields were important or not important. So I expected to see either a flat line, not important, or they are important, a line that increases as we increase the magnetic field strength. I didn't expect to see something with a hump in the middle. That's confusing to explain. That means that magnetic fields, planets have a sweet spot magnetic field, a magnetic field of just the right strength to maximize escape. And if the field gets too strong or too weak, then the escape rate goes down. It turns out that the planet loses less atmosphere. This seems strange and like our group is wrong, but it turns out other groups around the world, other groups in the MACH team are getting the same result. Those results differ from each other in minor ways, but the qualitative result seems to be holding in these simulations. So let's start to wrap up here. Where are we going next? Well, we have this science center. We have 17 people and they're graduate students and postdocs. We're having tons of fun. We're learning each other's language because we have people from the Earth community, the Mars and Venus community, and even people who study exoplanets. We have modelers and observers and theorists, and all of us use slightly different jargon in our own subfields. So a lot of what we're doing is educating each other and learning how to talk to each other, but also doing the kind of work that I just showed you in order to construct a framework to figure out how much atmosphere should escape from an arbitrary planet. So one of my main goals is to make sure that press articles like this don't appear anymore unless we know that this underlying statement is true. So Earth-like exoplanets may have magnetic fields capable of protecting life. And that's because the magnetic field protects the atmosphere from being lost to space. This is what gets written in scientific press releases and science communication, because people have assumed this is true for decades now, but it's not necessarily the case. It's something that we're questioning. Even more recently, 2019, and slightly embarrassing because I'm pretty sure I'm quoted in this article about MAVEN results. Why is Mars red and dead while Earth is blue and alive? The reason is its magnetic field disappeared and the solar wind stripped the atmosphere away. It's true that Mars lost a lot of atmosphere and that may have changed the habitability of that planet. But how important the magnetic field was in that process is something that we're still trying to figure out and that I'm hoping to spend the next 5 years answering, or less. I'd be very happy with less as well. Also, for the exoplanet community, I said that this is important for planets around other stars. We know of thousands. And in the next decades, we may be able to measure the strength of magnetic fields on planets orbiting other stars. And we can do that through a couple of tricky methods that I won't go into right now, but for really big planets, brown dwarfs that are partway between planet and star, we already have evidence that we can detect the magnetic fields on those objects. Not only that, we have definite evidence that atmosphere is escaping from exoplanets. We have observations that can't be explained any other way. Even though we can't image the planet, we can use our telescopes and observations to tell us that atmosphere is escaping. So linking these two things for exoplanets is something that we may be able to do, and we should be able to do observationally in the coming years. And being ready with an answer about whether magnetic fields are important is something that seems worthwhile to do now. So the last thing that I'll say here is that we'd like to construct something like what you see on your screen. We'd like to have, a way of setting a dial to the size of the planet and the strength of the magnetic field and the brightness of the star and the distance of the planet from the star, and set these kinds of things to arbitrary settings and let something go beep, boop, 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 and spit out an answer and tell us how much atmosphere that planet is losing, how much it has lost over time, and whether that planet could still be habitable today. This seems like a really fun thing to think about, and I'm happy to be doing it. So thanks a lot for your attention. There's a ton of work for us to still be doing, and I am happy to pass it back over to Amy, our moderator, and take questions.
Thank you so much. That was fantastic. You're so clear. Thank you. I'm going to start this off with a question of my own. So I've been studying the planet Mercury for many years and was on the Messenger mission. The planet Mercury is a rocky planet, closest planet to the sun. It does have a magnetic field, so I was surprised it wasn't included in your analysis. Will it be, or?
So it may be. Yeah, so this is a great question. There's some planets I didn't talk about tonight. So on one end of the spectrum, Mercury and the Moon, two rocky planets with very, very, very thin atmospheres, one with a global magnetic field, one not. What can we learn from them? The other end of the spectrum, giant planets like Jupiter and Saturn as well, that have strong magnetic fields. What can we learn from them? So we'll be folding results from those planets into our analyses, but our focus is on thinking about the rocky planets with substantial atmospheres today. So I would characterize my answer as saying we're going to use the lessons from Mercury and use the lessons from Jupiter to inform our understanding of the differences between Venus, Earth, and Mars, and even a little bit larger than Earth type planets.
All right, thanks. So I have a number of questions and I'm going to try to get through these. One of the questions is pertaining to the inner planets again. Why does Venus, with no magnetic field, still continue to have such a dense atmosphere?
Yeah, I love that question because it seems like, you know, everything is unraveled right then and there, just knowing that Venus doesn't have a magnetic field and yet still has a big, thick atmosphere today. And I have two responses to that question. And, you know, these responses are conjecture. They need to be verified, but they seem reasonable to me. Number one, Venus, number one, we've only talked about atmospheric escape tonight, but the state of an atmosphere at any given time is influenced both by the escape, what's leaving, and how much atmosphere is being added. And on planets, you add atmosphere from below through volcanism. And Venus is a big planet, the same size as Earth. Okay, for those of you who like Jupiter, it's not a big planet at all, but for terrestrial planets, it's around the same size as Earth. Still volcanically active today, we're almost certain. So Venus is constantly pumping new atmosphere in. And so in that sense, it's fine for Venus to not have a magnetic field, yet still have a big atmosphere. A second aspect to that answer is the Venus atmospheric surface pressure today is 92 bars, 92 times thicker than Earth's atmosphere. Say atmospheric escape on Venus has removed 5 bars of atmosphere. That's a lot of atmosphere, 5 Earth atmospheres. Who cares for Venus? Okay, it's got 92 today instead of 97. Atmospheric escape removed a lot, but it still has plenty of atmosphere left over. Whereas if Mars, a much smaller planet, had lost 5 bars of atmosphere, leaving the puny one that we see today, that's a really big deal. So it suggests that atmospheres are complex systems. I've confined myself and my discussion to thinking just about the escape piece, but we also have to think about what's being added as well.
Okay, so there's a couple of questions in relation to the shape of the escape, not the shape, but why is most of the escape at the poles?
Right, okay, this is a great question. So, and there are two aspects to this. Number one, the escape isn't always at the geographic poles of Mars, the North Pole and the South Pole. But the escape does have this pattern where a lot of it comes off one part of the planet very quickly, and some of it trickles around the rest of the planet. And this whole pattern, imagine me with a unicorn horn or a mohawk and some sort of beard that's swept back. This whole pattern can dial around in different ways so that most of the escape isn't always coming off of the poles. It actually moves from place to place. The orientation of this pattern is influenced by the electric field in the solar wind. So you have flowing charged particles. Those flowing charged particles are carrying a magnetic field. Those two things together create an electric field. And if the magnetic field in the solar wind changes its orientation, then the electric field changes its orientation, and all of this escape dials around to leave from a different direction from the planet.
Okay, so as far as exoplanets, is there any way at all to determine if they have magnetic fields?
Yes, there are multiple ways that people are considering right now. One way is to look for signs of aurora on those planets. And aurora don't always have to occur at visible wavelengths. They can occur in the ultraviolet, and depending upon the strength of the magnetic field, we expect the wavelength of the aurora or the energy of the aurora to vary. And so that brown dwarf example that I showed a couple slides ago is actually a detection instead of emission light coming from an exoplanet that we think is related to aurora. Another way to go about this is to look for, basically look at different wavelengths of light, observe the planet, even though it's one dot in the sky, you can't take an image, it's just a point source. You look at that planet in many different wavelengths of light, and it turns out that if you have an atom like hydrogen in the atmosphere, that atom will absorb or emit light at very specific wavelengths. And if there's a magnetic field present, then it turns out that very specific wavelength splits apart. And there are two wavelengths of light that get emitted there. That's something called Zeeman splitting. And so when you see your normal emission from hydrogen instead appearing as two peaks, that's an indication that there's a magnetic field present. And the separation of those two peaks tells you how strong the magnetic field is. So people are proposing and trying right now, and may have recently been successful. I'm not sure if that has been through peer review yet, in using this technique. A third technique is to look for something called a bow shock in front of the planet. Imagine as the planet is orbiting the star, there's the solar wind coming at the planet, and it ends up splashing around the planet. We saw that in some of our videos tonight. You could consider that kind of boundary, roughly speaking, I'm approximating here, something called a bow shock. And it turns out we may have ways of telling whether there is a bow shock in front of a planet. When the bow shock is really far from the planet, that could be because that planet possesses a strong magnetic field. So people are trying that method as well. So we have at least 3 different methods that people are trying to use to determine a magnetic field. There's a fourth one as well, and that's when the planet has a magnetic field that connects back to the star. It turns out that that can create variability in the light coming from the star, almost like a sunspot, but something that varies with the orbit period of the planet. So people have also used that method to try to detect magnetic fields. So at least 4 different ways that I'm aware of that people are trying.
Okay, great. What's the role of gravity in your picture of atmospheric loss?
Gravity is important. So gravity is what holds an atmosphere to a planet. The bigger the planet, the stronger its gravity is, and the harder it is to take away an atmospheric particle. It's way easier for a comet to lose its atmosphere than it is for Jupiter, because Jupiter is very, very big. So in this question, do habitable worlds require magnetic fields? I don't have a firm answer yet, but I think the answer is going to be it depends on some level. It depends upon what size planet we're talking about, because all of this has to compete with gravity trying to hold the atmosphere in. One big reason that Mars may have a small atmosphere, but Venus a big atmosphere, is that Venus is larger than Mars. What we're trying to figure out, though, is what role the magnetic field plays in that whole picture on top of what gravity is doing.
Okay, so does the presence of a magnetic field imply that a planet has a molten iron core?
Usually, yes. So a big dynamo magnetic field like Earth's usually implies a molten core. And that's because at least at the introductory planetary science textbook level, there are 3 requirements to get a big magnetic field like that. Number 1 is, electrically conducting fluid. So that would be a molten fluid where electrons can move around quickly in that fluid. Number 2 would be a source of heat, so convection happening. So that means you have heat at the bottom and not as much heat at the top, and that sets up convection cells like in a pot of boiling water. And that allows that molten material to kind of twist and tangle itself up. And then number 3 is rotation of the planet. And the rotation of the planet creates forces called Coriolis forces that end up twisting things up even more. And all of that together creates a big magnetic field. So when you see a big magnetic field, you usually assume that there's some molten electrically conducting fluid inside of a rotating planet. For those people who actually simulate dynamos and understand dynamo theory, they have caveats to what I just said.
Okay, there's a question about the hump that you see. And are you hoping to collect actual data that matches those simulations? I'm sure you are, but what's your next step?
Yeah, that would be great. I mean, the simulations and observations both work best when they work together, when you can use the observations to help you form some deep understanding of how the processes work. And then you can successfully incorporate those processes in a computer simulation. And it all hangs together. That's when you can feel really certain that you're right. Validating that model result is going to be a bit difficult. If I was an evil superhero, then I would be able to turn Earth's magnetic field strength up and down, or the Mars magnetic field strength up and down, and send Maven to the planet each time and record those observations. That's not something I can do. Another thing I could do is find a lot of different planets that are the same as each other, maybe exoplanets, and only differ in their magnetic field strength, and compare their escape rates. That seems a long way off as well. The third thing that I think we can do is use the Mars kind of analysis, a single planet that has magnetic fields of different strength in different places, and see if we can reproduce that hump. And so some of the results I showed earlier are suggestive that that kind of trend is actually correct.
All right, great. Well, I'm going to cut it off there. There are a number of questions that we didn't get to tonight. We have a copy of those in our recording, and we'll see if Dave might have time to get those questions answered. But we appreciate you giving this talk this evening, and thank you so much for joining us.
Yeah, thanks so much for having me. This was fun. And if you didn't get a question answered, my email address is actually pretty easy to find on the internet because of my crazy last name. So you can shoot me an email with the question and I will get back to you on some time scale. It might not be in the next 24 hours or anything like that, but I'm happy to try to answer. So thanks again for having me.